Homeostasis is a term that translates literally as same standing still. But that's not what homeostasis actually is. Homeostasis is the ability of the body to dynamically change, not stand still, but to change based on the external and internal stimuli that it's experiencing moment by moment. It's a complicated and amazing set of physiological responses that allow us to carry on with day-to-day life that is constantly being done without you even having to think about it. Now, this is a fussy lesson. This is a lesson that's full of details and making certain that every single aspect of the homeostatic feedback loop is being defined correctly, and therefore examples are important. So the first thing we write down is a variable. We basically write it as a straight line. A variable is the factor or event being regulated. And then we think about the fact that a stimulus is going to come along either from outside of the body or perhaps from inside of the body, and is going to cause that variable to either go up or down. And so the variable is going to be something that is measurable, and then you can measure it as being decreased or increased, depending on the stimulus that came along. A stimulus is defined as anything that changes a variable. I think at this point, I'll start giving an example of this. So the example that I'm thinking of is, it's a good example because it's one of those where actually everything is well defined in the entire system. It's not always easy to suss out exactly what's happening inside of the system, but this particular example is really good at that. There's clear definition at every point along the way. So the example that I'm going to give is the variable of light entering into the eye. You have to have a certain amount of light to be able to see, but you can't have too much light, because if you have too much light, then it becomes actually a painful experience. You hyperstimulate the sensitive cells at the back of the retina, the back of the eye, and that can cause problems. It actually could ostensibly lead to permanent damage if you continue to shine a bright light into the eye. So the variable here is light in the eye, and the stimulus is going to be a bright light shines into the eye. Now what's going to happen is the variable then is going to be changed, and I'm going to show the two different ways this is going to happen, but we're only going to explore the upper way. So I'm just starting the cycle down at the bottom, but you can go ahead and fill that in later. The first thing that's going to happen is the stimulation that occurred to the eye is going to be sensed by a receptor. In this example, it's super easy. There are photoreceptors. You may know them as rods and cones at the back of the eye. They will actually be sensing the amount of light that comes into the eye. The next thing we're going to do is we're going to draw another arrow, and we're going to define this as the afferent pathway, the afferent pathway. I always kind of emphasize the A there because there's going to be an efferent pathway in a moment that sounds very much like it. The afferent pathway, perhaps you want to remember this by saying approach. This is the pathway that approaches the next structure in line, which is going to be the control center. Now, in our case, the afferent pathway is well defined. It is going to be the optic nerve, cranial nerve 2, that leads out of the back of the eye and then sends a signal to the brain. Now, the control center, also called the integrator, oh boy, I tell you, these green markers. I auditioned a few different green markers. This was actually, believe it or not, the best one. Anyway, so the control center, the integrator, this is where you analyze the input coming from the receptors, and then this in turn determines the appropriate course of action. As we've already said, in our example, the control center is going to be the brain. That oftentimes is the case. There could be something in the central nervous system, either the brain or the spinal cord, where there is some input put into the system and then an output is put out, and then you decide what happens next. That's where the decision is actually made. Right, so our next pathway is going to be the efferent pathway, the efferent pathway. You can see efferent and afferent sound an awful lot alike. Now you might want to remember efferent by saying exit. Remember afferent is approach, efferent is exit. So the efferent pathway is going to be bringing the signal. The decision that was made at the control center is now going to be brought to the next thing in line, which is the effector. Now, in the case of the example that I'm given, the efferent pathway is also well defined. This is going to be the oculomotor nerve, cranial nerve 3, which is responsible for moving the next muscle that I'm going to be discussing in a moment. Our next box is going to be the effector. We define the effector as the responder. It allows for the response to the output from the integrator, from the control center. I don't know any exceptions to this. Generally speaking, the effector is going to be either a muscle contraction or a glandular secretion. Again, I don't know. I'm sure there's other things that happen at the level of the effector, but those are the two that I know about. It's either going to be a muscle contraction or a glandular secretion. In this case, it's going to be a muscle contraction. So it turns out the colored part of your eye, the iris, is a muscle, and the muscle of the iris is able to cause a closure of the hole in the middle of it, which you may have heard of before, called the pupil. So this is what we call pupillary constriction. And when a signal is sent along the oculomotor nerve, there's a number of things that happen, but one of the things that happens is that the iris causes the pupil to close up a little bit. Pupillary constriction. And this is the response that we are desiring. Take a look at what the original stimulus was. Too much light coming into the eye. The response is going to be a muscle contraction that allows us to close off some of that light that is coming in. Now, this entire homeostatic feedback loop that we're looking at here is describing negative feedback to a homeostatic imbalance. Something came along and irritated the eye, and the eye is going to react to it. Now, on the other side of the coin, basically the underside of this variable line, there's also a stimulus which would be dim light, for example. There's too little light coming in, and in that case, basically the opposite thing would happen, where you try to open up the pupil and you'd have other various reactions to ensure more light coming in so that you'd still be able to see. So this indicates that there's sort of a range of visible light that is appropriate for your eye to receive. Too much light coming in and it risks damage, but too little light coming in and it's also an issue. You wouldn't be able to see well. Either case, too much light or too little light, and the body's response to it, either case is considered negative feedback to a homeostatic imbalance. That can be a little bit deceptive because what we're doing with negative feedback is the variable changes in an opposite direction of the initial change. So the initial change goes up, the variable, the response is to come back down. If the variable goes down, the response is to come back up. And that can be a little deceptive. Oftentimes students are a little caught up in the idea that, for example, if your blood glucose levels get too low and you bring them back up, in your mind you want to say, oh, that's positive feedback to a homeostatic imbalance. But in reality, that's still negative feedback. You're still bringing it back to something that is appropriate, a variable that is a range that is appropriate for your body, where you have the appropriate amount of light or the appropriate amount of sugar. Another really good example of this, by the way, is body temperature. You can kind of look over examples of the body temperature regulation. All the different parts of the feedback loop are present either in a way that goes upward, where your temperature goes up too high, or when your temperature goes too low. All of those things, when you're getting back to 37 degrees Celsius, which is appropriate body temperature, then you're getting back to it. That is negative feedback. Again, whether your temperature is too low and the response is to bring it back up, or whether your body temperature is too high and the response is to bring it back down. In either case, it's negative feedback. But there is such a thing as positive feedback to a homeostatic imbalance, but it's just really, really different. It's a separate, kind of a special situation. There's a few examples of this that I can think of. So with positive feedback, the original disturbance causes a change which proceeds in the same direction as the disturbance. This is the difference. With the negative feedback, you want to get back to the homeostatic range as quickly as possible. But with positive feedback, it's actually appropriate to continue to amplify or cascade the response. So same as before, you're going to have a variable. It's important to define, first of all, what your variable actually is. And there's going to be a stimulus which is going to change the variable, and it's going to be measurably changed in the positive direction. Basically, it's going to elevate the levels of something in the body. Now, what happens with positive feedback is you continue appropriately, you continue to ramp up the response. The more elements of the thing that are present, the more response there is. And it keeps continuing in a positive direction, taking us away from what we would consider to be a homeostatic level, because it's actually appropriate to move away from the homeostatic level or the straight line for a little while. Eventually, however, there is an end to this. And when the signal ends, then eventually, it doesn't happen right away, but eventually you will bring your levels back down to the level that you started with. Okay, examples. Well, I'm going to give the example of childbirth. So we all understand the concept that when you are in labor, the labor pains basically consecutively get harder and harder. I was going to say worse and worse. It basically contracts harder and harder until finally the baby is born. That would be the end event there. And then eventually you would stop, you'd stop your labor pains. Well, pretty much right away for the most part, once the placenta is delivered, the labor pains end. So the reason why you start to have labor pains is that you have a full-grown baby pushing down on the cervix. The cervix is the lower part of the uterus, and when the baby weighs enough, basically it pushes down on the cervix. Now that sends a signal to the brain saying, this pregnancy is close to the end, and therefore it's time to begin labor. There's a structure just inferior to your brain, the posterior pituitary lobe, that releases a substance, a hormone called oxytocin. So we're going to use oxytocin as our variable. So the stimulus is pressure on the cervix from the baby's head. And then what happens is oxytocin is released through this signal mechanism. Now the oxytocin will do various things around your body. Remember that oxytocin has sensitivity, has receptors and therefore sensitivity in the brain, the mammary tissue, and also in the uterus. In the walls of the uterus, there are these muscles called the myometrium, and they have receptors for oxytocin. So the oxytocin will go and interact with this muscle, and the muscle therefore will squeeze the baby downward against the birth canal. And then, guess what? The pressure against the cervix is that much more. And the feedback to the brain is that much greater. And then more oxytocin is going to be released from the posterior pituitary lobe. And then the next squeeze is going to be harder. So if we are just measuring, there's a number of things we could measure in this case. I choose to measure oxytocin levels in the blood, but you could also measure the squeeze of the, you could measure the squeeze of the myometrium and how hard it's squeezing each time. That's something that's actually measurable. But you see how, this is a really good example of how, it's kind of a complicated story, but you can see how it's sort of this positive, like upward spiral. The one thing causes the next to be greater, which in turn causes the next to be greater. The more pressure on the cervix, the more oxytocin is released, you see? But the more oxytocin is released, the greater the squeeze of the myometrium, and therefore the greater the pressure on the cervix. It's actually a really good example of positive feedback. It's this special event, right? We're not talking about regulating body temperature or regulating your blood glucose levels or regulating the amount of light coming into your eye. We're talking about a special event, childbirth. Doesn't happen that often. This is a good example of positive feedback because you have this up and up and up and up thing, and then the end thing is the baby is born, the placenta is delivered, no more contractions needed, therefore your oxytocin levels will gradually begin to come back down to something in the range of what's a homeostatic level under normal circumstances. So other examples of positive feedback would be clotting a wound when your blood vessels have become damaged and you're bleeding. That clotting action has to keep on happening and going up and up and up and up until finally the wound is basically blocked. The bleeding is blocked, and then that could be the end of the signal. And then we can bring the clotting agents back down. So in that case, you'd be measuring clotting agents such as fibrin. The fibrin levels will keep getting higher and higher as long as you're still bleeding out. And then as soon as you stop bleeding, the fibrin levels drop back down. And necessarily so. Fibrin is a protein that clots wounds. It causes coagulation. You can't have it circulating freely. All right, so we've given two different scenarios here. We have negative feedback to a homeostatic imbalance in terms of kind of regular old things that have to be regulated on a daily basis, on an hour by hour, a second by second basis. That would be a negative feedback situation. If the thing gets too high, it's brought back down. If the thing gets too low, it's brought back up. The second scenario is positive feedback, where you keep cascading or amplifying a response as long as this special event is occurring inside of your body. And then once the event has ended, you can bring the levels back down to a more normal, if you will, level. But the third scenario is this. If you have the inability to regulate something properly, then you probably have a disorder. Disorders are sometimes called homeostatic imbalances. I usually just call them disorders because it's a little bit less wordy. So a disorder is a situation where you cannot, for whatever reason, you cannot respond to a homeostatic imbalance properly. So for example, if you cannot properly coagulate your wounds, you may have a condition called hemophilia, and you are at risk of bleeding too much because you can't stop the bleeding. You can't conduct hemostasis, or the stoppage of bleeding. Another example would be the inability to regulate your blood glucose levels. You might have a condition called diabetes mellitus, where if your blood sugar levels get too high, you cannot bring them back down. So you can see how you could have an erroneous situation of positive feedback, blood clotting, or you could have an erroneous situation of negative feedback, for example, on the inability to regulate your blood glucose levels. So a disorder would be the third situation. Your body cannot do what it's supposed to do. You may need medication or some kind of a treatment to help you along with the process.